presentation. I'm very happy to be here. Thanks for joining, everyone, and hello. So, as I said, I'm presenting. Sorry, as Moshe said, I'm presenting this paper today that was in Wine last year, and is joint work with Yorgos Amanatides, Yorgos Birnbas, Federico Fusco, Philip Latzos, and Stefano Leonardi, who's also my supervisor. First, I'd like to introduce a little bit, of course, just to see what's going on. So we're talking about fairness here. And fairness is a pretty subjective concept, as you might know. And of course, there are a lot of applications where you like to be fair. For example, in a divorce, if you want to divide the goods that you have between the partner and you, it would be nice if everyone was feeling like he was treated fair in the end. Or dividing an inheritance, or all of the other applications I mentioned there. The most prominent one is probably the one of cake cutting. So for example, if you have a birthday cake at the office, who gets which slice, how do you cut it, all of these things would be subjective to fairness. So everybody wants to be feeling like he's been treated fairly in the end. Now, it's not very clear what does that mean in practice. There are some things we could imagine, and I've just put a picture for overview. For example, if we look at the upper left, we might just have some goods to allocate or items to give away, but it's probably fair to just not give anyone anything, right? So the guy and the girl, they both get nothing. You could consider that fair, because no one is better off than the other. However, it's relatively impractical because they will both still not be very happy in the end. Or if you look on the right side, if you have some things to divide, you can just give both of them half of everything. But they will not really know maybe what to do with half a skateboard or half a ball. So this might be impractical too. And then there have been some ideas for different scenarios and with different histories, what to do. If you look on the lower left, for example, you could imagine you're the tie guy and you have the red valuations on everything in the allocations there. Now you get 21 of value, but the girl has 22. So this should make you dissatisfied, right? You should probably want to get half of the value overall. So that is a way you can make a definition for fairness, or you can base it on, if you look at the lower right, something other than that by, for example, saying, okay, if you're the tie guy and you would prefer what the girl has over your own allocation, that's probably also not fair and a reason to be unhappy. So basing on that, there are some other notions, and I'll just give a short intro. So what we'll assume here is that we have no free disposal. If you look at the upper left again, well, it doesn't count to just throw everything in the trash, right? That's fair, but not great. And also we will have a complication of indivisible goods. If you look at the upper right, you can't just cut things in half. They're useless if you do. Now, we will look for this talk on only one type of problem, and that's the following one. Let me just introduce it now so I don't have to do everything else in more generality. Let's say we have a number of goods in the set M, and we have some agents in the set N. Now, each agent has some additive valuation. Just for every good, he has a value, and for every set he might get, well, he will have the value that is just computed by adding up the single ones. And an allocation is a partition that just says, well, the first agent gets this, the second agent gets this, and so on. So we will look only at that case. Now, if you come back to the fairness, let's say we could look at first to the lower left, where we had this value-based idea of saying, if you're the guy, you want to get half the value. There is a notion that is getting this kind of inspiration by just saying, we call an allocation proportional if each agent receives at least 1/n of his total valuation on all goods. So in this case, half. Then there is also another notion that would be coming from the same direction, which is called MMS. It will come up only a little bit later, and it's not that important. But just to introduce, maximum share fairness is defined as the following. So if you're the guy and you make one bundle for each agent, so n bundles out of the goods, and we tell you beforehand, well, we will assign you the worst one of those. Then you're going to try to make them as equal as you possibly can, right? To make the worst one not so bad. So this is also a useful thing to say. And based on this, we just define maximum share fairness as it's said there. So it's MMS if each agent receives at least the value he would when he optimally divides all goods into n bundles, knowing he will get the worst of them. So these are some notions that are coming from this part of the picture. On the other side, the natural thing to consider is envy-freeness. So you could say an allocation is envy-free if, again, being the guy, I would not prefer what she has over my own bundle. And if that holds for all the agents, you like best what you already have, then it's envy-free. Now there are relaxations because we have, as you remember, these two complications from above. You can't cut items, you can't throw them away. So there's another thing we can look at, and that's envy-freeness up to any good. So if you can't be envy-free really, well, you might be almost envy-free in the sense that I like what she has, but if I take away anything from her bundle, then I would probably prefer my own. This is up to any good that we might erase. So even if you take the worst one out, then everybody prefers their own stuff. One can further relax this, and we will use this notion actually centrally in the talk to get EF1, which is meaning, well, at least if I take the best thing that she got out of her bundle, then my bundle is better. So this is EF1, and we're going to work with that a lot. Okay, this was just some overview. And what we're doing in this talk is actually, we are combining two very common goals, which is first this fairness thing that I just introduced. And then we have strategic agents. So these might be misreporting what their values are for the items in order to get a better assignment. So ideally what we would want to combine is one of these fairness notions, or and incentive compatibility or truthfulness. This is defined as a mechanism or algorithm, but we call it mechanism here because people can lie, is incentive compatible or truthful if it's the best thing to do for every agent to report the actual values as they are, not lie on anything. Okay. So combining these is a nice goal, of course, because you would like to be fair, and it only makes sense to be fair if you're fair with respect to the actual values people have in the end. The question is, can we do this? And sadly, it's very, very hard to do. If you look at this paper, this is incompatible for even if you just have two players and for a lot of fairness notions. So you can see impossibility results there if you're interested, which means we had to modify that goal a little bit and say, okay, if we can have fairness, not together with truthful mechanisms, but say if we can have fairness where, well, the equilibria of a non-truthful mechanism at least define fair allocations with respect to the true values. That would also be nice. So if you assume you have this algorithm or mechanism here, and this produces at some point an equilibrium, everybody is trying to get better and better and better until you reach this equilibrium. No one can improve anymore. If that would be fair with respect to the actual true valuations, even if people lie, this would be great. Right? And actually, we have done something like this, of course. which is why I'm presenting today. And we have done it for this envy-freeness up to 1 unit, EF1, which you can see in the picture. So if we take out the skateboard, the guy prefers his own set. And we have shown that you can combine this with truthful equilibria in the sense that there is an algorithm that even if you lie to it, will produce an outcome that is an equilibrium, where we only talk about pure Nash equilibria here. That means no one can report differently and gain more value if you fix the reports of everyone else. But this Nash equilibrium is then with respect to the actual valuations, even if someone lied. It sounds a bit weird, so if you have questions, stop me at any time. Otherwise, I'll try to explain all the ingredients. Okay, so the algorithm for which we did this is the following: round robin. Extremely exciting, I know. It goes as follows. You have the red valuations and the green valuations on the items. And now everybody, according to a fixed order, gets assigned the best item they can in that order, and then you repeat. So first, player 1 would pick this for 20. Now it's player 2's turn. It's going to have this, and so on. So that's the whole algorithm. As I said, exciting. And for this very simple one, actually, we did show this thing where the equilibria are fair with respect to the true valuations. However, just to see that it's not completely simple, let's have an example that shows that if you say the actual truth on your valuations, you don't really get into an equilibrium automatically. So let's say we have the situation as above. Player 1 and player 2 have the valuations that I put there, and the algorithm does this. So player 1 picks. Now player 2 picks, he liked the skateboard, and now player 1 picks again, right? Now, if we modify the valuations as we did before, but player 1 now lies and reports this dark red stuff in the lower part. So he pretends he wants the skateboard more than, she pretends she wants the skateboard more than the box with the cat. Well, she will get the skateboard first now. Now player 2 picks, he will get the ball, and then it looks like this. Now, if you look at the actual true valuations of player 1, in the upper part, it's 10 for the bundle. In the lower part, it's 11. So clearly, it was worth deviating, right? She did gain something. So this was not an equilibrium. This means the lying part, it will actually occur in the algorithm. So this is in theory pretty bad. Okay, we've established that there's something to do. And let me just quickly present the main result in written form so it makes more sense. We know from the literature that this round robin algorithm that we're looking here is just always producing EF1 allocations. So when presented with the true additive valuations and no one lies, the outcome will be EF1. And then we also know that for any instance of the problem, this algorithm always has a pure Nash equilibrium. So part of this we had to show in the paper, but it wasn't much work. So basically this was already known. What we did show and what our main result is the following. So the round robin mechanism, that is just the same algorithm, but people might misreport, produces truthful EF1 pure Nash equilibrium. What does that mean? That means for every instance of the problem, the equilibria of round robin are actually fair, but with respect to the true valuations of the players, even if they're lied, weirdly. And I'd like to give some insight on why and how this works. But let's make sure first everybody got the idea of the result. So what it basically says is only, yes, it might be beneficial for you to misreport your values in this algorithm. But at the point where you are at equilibrium with all the other players, no one can deviate anymore. At this point, the allocation is fair, and it's fair for you actually with your actual values, not the ones that you lied about. So this is a nice thing, of course. And well, one key observation that it's based on is the following. If you recall, the algorithm just goes player 1, player 2, player 3, everybody picks something, and then repeat that, right? This is one round, 1, 2, 3, 1, 2, 3. And doing that, we get this fairness for everyone in the sense of having EF1, but we even get EF as envy-free for the first player. Let's see how that goes. So let's say we are the player 1, that's the red one, and we have the red valuations there. Now, what does the algorithm do? In the first round, it takes the very biggest overall item that we have in the red valuations and gives it to us. We're very happy with that because now in this round 1, surely no one else gets something better, right? They can only get lower values because, well, we got assigned the highest one. Now in the second round, what do? Again, we pick the highest value from the leftover items. Here it's the 9. And clearly everybody else has to pick from the rest. So they're not better than us. And then the next round, it's the same thing. There's a leftover set of items. We pick the largest one. Everybody else is worse off. So this means we cannot envy any of these people because in every round, well, they get something worse than we do. I think this part is pretty clear. And then for every other player, what happens is, let's say we are number 3. Let's ignore the part of the algorithm that we've done before it's the first time that player 3 picks. That means everybody else already has one item, that's fine. But now, assuming this hasn't happened and player 3 is actually the first to go, well, again, in the first round, which is now 3, 1, 2, he picks the biggest thing, and in the second round, and so on and so on. So that's envy-free for him, except, of course, the items we have ignored in the very beginning, right? And this is why for every other player, the algorithm isn't envy-free, but it's envy-free up to one item, the one that we've ignored in the beginning. So this is why it's so nice and easy to understand that this algorithm provides this fairness guarantee. Okay, let's do a warm-up and show the results for 2 players. Say there's only the Thai guy and the girl, and we have no more people. And remember that, you know, the first guy is actually envy-free, so he likes his set better than hers. And for her, it's EF1. Now, what we want to show is if the algorithm produces an equilibrium, so everybody plays their best response, fixing the other valuations. And we have that round robin has made this algorithm, this equilibrium. Then, of course, we can analyze something. Let's do that. So we fix an equilibrium. We know that agent 1 is playing the best he can, right? We also know that agent 1, because he's agent 1, he is envy-free. And what does envy-free mean? It means that in his valuation, he's getting at least as much value as agent 2 does. And he can achieve that by simply saying the truth. So picking the biggest item in every round. Now we get that the valuation of agent 1 for his own stuff is, of course, greater than the valuation of agent 1 for the rest of the stuff, which is what player 2 gets. So we have it's at least half of the overall value of all items. And this is it. Now for the other agent, well, she again can, after we ignored the first item that agent 1 picks, can pretend she was agent 1. And then it holds similarly. So for her, well, it's EF1, which is pretty easy, right? So apparently for 2 players, this equilibrium, even if people lied, whatever, just because they're playing best response, and there is a response, i.e. the truthful one, that will give them half the overall value, well, just because of that, it's going to be fair with regards to the actual valuations. But sadly, this works only for 2 agents. Because if you have more of them, then just because you're having some fraction of the overall value, you don't know much about fairness. And this is why we have to do it differently in the general case. I'll do my best and give some flavor of how this proof works too. It's pretty technical and has a lot of parts and lemmas, but I think the insight that is behind it is nice and has a very fun structure to follow. So let's see. We have again 3 players in the picture. And let's say the evaluation of player 1 is the actual red one, the lower one that says V1. But player 1 bids say B1. So this is the situation we have. And the proof is in principle based on this insight we just had, where everything is envy-free from the perspective of player 1. That means we will just follow player 1 and then try to do some manipulations to show that every Nash equilibrium also is fair with respect to his true values, so the lower ones. This is the idea we're going to follow. And the proof uses one main technical lemma. This is, I think, not very intuitive, but let's try and go through it. So assume B1 is the bid or the report that agent 1 plays, together with B2, B3, and so on, the other bits. And then there exists a valuation function V1 star, which is not actually the true one of player 1, but it's also not necessarily the one he reported. It's something, but it has the following properties. First, round robin produces the same allocation as 1 till Sn on the actual bit, which is B1, B2, B3, and so on, as it does if we replace the bit of player 1 by B1 star, where B1 star is the truthful bit for V1 star. I'm sorry, I forgot to put that in writing. So this is just the representation, correct representation of V1 star. And then we also want that for his own bundle S1, this valuation function V1 star for player 1 is the same as the actual true value he has, V1 of S1. And finally, lastly, for all the items that the player 1 does not get, we also want V1 star to be the same as V1. So that's just truthful. What does that mean? That means that for the items in the bundle that the player 1 gets, V1 star might be anything, but in some it's going to be correct, right? And for all other items, we have the actual true values. And now we would like to construct this V1 star and show existence because it has the following property. The allocation there is, if we have all the properties, is envy-free with regards to both. So V1 star and V1. Why is that? So for envy-freeness, we only need that the bundle that he gets is better for him than anybody else's bundles, right? So that means because he still has the same overall valuation in V1 star for S1 as he did in V1, his own bundle is worth the same to him. And then, of course, for every item not in there, he actually has his true value. So that means because he's player 1 and this is round robin, well, it's going to be envy. And it doesn't matter if we switch value around among the items that he gets anyway. This is the intuition. Now, what one can say about the algorithm in an intuitive sense, and maybe as a first idea, would be possibly the following. So why do I not bid truthfully? Why do I lie? Well, definitely, if you look just at the last round, the last time player 1 picks, well, it's fine if you just do it truthfully. Why is that fine? So if I say okay, I have a valuation of 3 for this cat, and the Star Wars box, well, if it was better, and if it was a value of, say, 5, then I should have picked the Star Wars box, right? It doesn't matter at this point, because later on in the algorithm, nothing happens anymore. I have no more turns. So in the last round, it surely makes sense to just pick the best item. So if I pick the cat and the cat is worth 3, then definitely the Star Wars box is worth less. Otherwise, this is not a good idea, and it's not a best response, and it can't be an equilibrium. So this is maybe a nice start one could think about. And then one could try to say, okay, if I can play my true value in the last round and just pick the biggest one, maybe inductively I can go back and I can do the same in the rounds before. This, however, does not quite work. And why does it not quite work? Well, we've seen this example. Let me see if I find it. This one here, where actually by lying, you can gain something, right? The only thing it means is, well, you have to lie already before the last round. So apparently this idea is not really enough. Where are we? Are we there? Okay. So we need something else, and we need something more to actually make this work. And to give you some flavor of what this something more is, let's do a new picture here. So we have this picture from before. And let's say I'm making a division into rounds. So we have round 1, round 2, round 3. We have kind of analyzed round 3. We know that there the B1 star, B1, they're all gonna be just truthful. Like why lie? It makes no sense, right? This is what we said. And now it gets a little more interesting, because what happens in the round before? Let's say in the round before, we had the above values. Look at the upper part first, maybe. Let's say, actually, these things are worth 8, 9, and 4 to us. But we did bid 15, 11, and 6. Now, what we need, if you recall from the lemma we had before, is to replace the bit B1 by a bit B1 star. That is the same as the true evaluation for every item that is not player 1's. So we know the ball must be 4. We also know the skateboard must be 9 in B1 star. So we replace 6 by 4 and 11 by 9. And now the problem is we can't really go and replace the cat's value by 8. This would be truthful, but it would mean that in this round, well, the algorithm wouldn't give us the cat, it would give us the skateboard, because that has 9. And we needed to preserve the same allocation, right? This was in the lemma. So to preserve the same allocation, you would at least have to bid 9 on the cat too. Maybe some epsilon more, but let's ignore that for now. So definitely the cat must have 9 at least. And well, if we now look at what player 1 gets in the last 2 rounds, that is not the greatest idea, because, well, we have 8 plus 3 as the real value for the 2 cats. And we have 9 plus 3 as the B1 star. So that's not legal. Why is it not legal? Because the third requirement was, let's go back to the requirements, to have that the value of the set that player 1 gets does not change overall. Right? This is number 2 here. So getting all 3 conditions seems not so easy. And we haven't done it yet, but we need to keep the 9 for the other conditions, so not much we can do. And at this point, what you could think about is the following. So actually, in the true valuations, light red, we do like the skateboard more than the cat, right? Yet somehow it was a best response for us to play to pretend we like the cat more. For this to make sense, it would have to have been somehow bad for us at this point to take the skateboard. Like, what if we take the skateboard? We gain 1. So we must lose something later on for this stuff to be a best response. Now, what if we take the skateboard and we lose something later on? That just means, well, someone later on, for example, player 2, picks something that we would have liked better. So for example, the reason that we didn't pick the skateboard and we left it for player 2 was that if we hadn't done that and lost 1 value by doing so, if we hadn't, player 2 wouldn't have gone for the box in the end, but he would have stolen like the cat from us. So it might have been because later on we would have lost some value, and that means essentially that there must have been a difference between the later values that was more than 0. So it wasn't just smaller, it was smaller by at least 1. Because if we lost 1 in the best response in the round before, that means somewhere later we must have gained more than 1. Okay, thinking like this, well, we can just go and fix the values in the following way. Now our problem is, for the 2 cats, we bid 12 when we should bid only 11, so 8 plus 3. And to fix that, we can now do this, right? If this was the situation, then why not reduce this bid? We still win. And well, because we still win, and this is the largest value, we haven't changed the allocation. Still, we have not changed any values for the things that player 1 doesn't get. But we are in check again with the sum of the values for the stuff that player 1 has. So essentially, the whole proof idea is to follow this. Oh my God, I need too much value now. What is happening? I did this as a best response. So somewhere later, if I took this better item, I must have lost this value. So now I can reduce my bid accordingly later. This is the whole idea. And now these, again, they check out to have the same sum. So we're happy. And roughly, as an overview, what happens is the following. So you try to replace the values in B1, that's the original bit, in an order preserving way by this B1 star. So you don't want to change the allocation, right? And you, of course, replace the bid values on the other items that you don't get by whatever your true value is, because that was in the lemma. And then you, if you can't make it work, for the sum of player 1's set, you follow a chain of events. And the chain of events is a chain and only a chain because of the following reason. You say, okay, if I had picked this other item, what would have changed? The set of available items would have been different by only 1, right? So you have to next check what happens if someone picks this 1 later that wasn't available before. And then what changes because he deviated from his original 1 to that 1? Well, again, there's 1 item that wasn't there before. So again, check if someone picks that later. And so on. This is what the arrows indicate. And this just makes a chain because, well, the adjustment you've done, it was really limited in effect on 1 item. And now, because we're lucky, somehow, if you actually add up the values and you use this property that round robin is envy-free for this player, which was based, of course, on the essential truth that in every round, player 1 picks the best, and he dominates all the values of anyone else in the same round. If you use that and use that repeatedly along this chain of adjustments, well, it works out and you can adjust in a way that preserves the sum of values in player one set. So this is how the result is proven. And as I said, it's a bit more technical and slightly annoying in the paper, but this is a sense of what's happening, and I think that's probably enough. And for me personally, this was very nice to see, because the structure of following these events on the chain through the whole algorithm is actually, it's not that hard. You just have to do some computations, and it gives a nice induction-like structure, which I think is really, as a core insight, it's really not bad to see, because it reduces to some simple things that you can observe, and there is maybe some hope to, apply this in other settings and to maybe find some ways to extend on the results. So this was our main one. And just to give an overview of the rest of the paper. So as you recall, maybe we had these different fairness notions based on people's ideas on how you could define fairness with values or with preferring one set over another. And we wanted to also give some other results to complement and see what happens there. So there are some minor ones that we also proved. I just put them here for completeness. Let's go through. So the first one is the one we just talked about. The round robin algorithm, it always has pure Nash equilibria. And these induce allocations, which are NB free up to one item with respect to the underlying true values. This was the main theorem that we just showed, which we did by essentially almost replacing the report by almost the true values. So how do we...
Rebecca,
Yes,
can you say 2 more words about how you derive the theorem from the lemma?
Okay.
Thanks.
Let me just find the lemma though here. Okay. Yes. So the lemma says you can take V1 star and the according bit B1 star, and you can bit that instead of B1 and get the same stuff as before, right? And now the 3 properties that we listed there say something like V1 star is almost V1. And it is not just almost V1, but it is exactly V1 with respect to everything that counts into NB freeness. So you have that V1 star has the same value for your set as 1. So your set is worth to you just what it is truthfully. And then also every item outside of your set is worth to you just what it would be in the truthful valuations. So what is the difference between these two? The difference between these two is, say, if I have this 10 and this 8 cat, the first 2 red items of player 1, I could maybe call them, well, 8 and 10 instead, or 9 and 9, or whatever, 1 and 17, right? I can distribute the value among player 1's set in whichever way I like, but everything else stays the same between V1 and V1 star. Now, how the values are distributed inside the set that I get all anyway doesn't really matter, as long as their sum is the same. So the definition of NB freeness is exactly the same formula for V1 as V1 star. And because I can report just V1 star, well, and I get the same stuff, this is a way to get the fairness with respect to V1 star, and therefore with respect to V1. I hope this was helpful. In very short, there are enough the same such that NB freeness is the same for both of them. Yes. moving back. Sorry, it takes so long. There we go. So this was the main result. And then we just had some look at some other things and found some things that we thought might be worth reporting. So as you've seen before, maybe it's always good to look at two agents because things are simpler. And we did for this cut and choose protocol of Cloud and Raffgarden, where they have, a modified cut and choose that is on a lexicographically minimal kind of allocation that they define. You can look it up in the paper. We just looked at that algorithm. So for that, you can always show that there are always PNEs, and these induce allocations that are actually EFX, which is the one notion that says you cannot take out the biggest, but you can take out only the smallest item of a player, and then you stop envying them. So it's a bit stronger. And even this maximum share fairness with respect to the underlying true values. So this works too, basically, with the same sentiment. And weirdly, the guarantee gets better doing so. So if it's not strategic and you just look at the algorithm, you don't have to have MMS. But now that you can lie, if it's an equilibrium and you're doing best response, we actually obtain that. So this might be surprising in case you want to do something with that specific algorithm. For us, it was mainly interesting to see, well, can you do anything with other routines than round robin? And then lastly, we have another result saying all mechanisms that have pure Nash equilibria for every instance with two agents. And these equilibria induce allocations that are always EFX. If you have this, then weirdly, these algorithms provide stronger MMS guarantees in the according allocations than generic EFX allocations would do. So there is a smaller equal that becomes a smaller, and we don't really know why. And appears that actually in this sense, it might be helpful to look at these strategic things. If you look above, then suddenly you get MMS by allowing this mechanism version of it. So these are some results that we also reported. But in addition, of course, we are working on doing some more in this direction because it is possible and not inhibited by these impossibility results I reported earlier. So
right.
this, sorry?
Yeah, sorry. Can I ask a question about the previous slide?
Of course.
The last point, when you say stronger MMS guarantees, you mean better approximation or just Pareto improvement? Or something else?
Oh, okay.
What does it mean, stronger MMS guarantees?
Usually it means you get at least as much as the worst bundle is if you make n bundles, right? So there you get a little bit more for some reason.
In the sense of just higher value?
Yes.
Okay, thanks.
So what we're working on now is to see what can you do. This was our first idea and the strongest one we're working on beyond this additive setting, because right at the beginning I said, okay, everything has a value. If I get a set of things, I'll add the values, right? And you can do more. So we have managed to do similar things when the evaluations are not additive, but say budget additive. So this means you can add up things in a set, but only up to some cutting point, and then everything else you put in will not be worth anymore. So there's a budget, you can spend that, that's it. For this setting, pretty much the same things work. And then a very helpful notion seems to be the cancelable set, which is taken from a paper of Michal et al., where they defined it, and it's very helpful for us too, which is maybe not surprising because it's related. But for these functions, we also did it. They basically mean if you take A and B, and A is smaller than B, and then you take one item and erase it from both, they won't change order, right? It's still A is smaller than B. So for these, it's also working. We've tried to do more and get to something like submodular or XOS or whatever we could. But these are hard to grasp. So our ideas there don't work as directly. So I'm very thankful if anybody has an input or maybe a feeling on how to approach this. And of course, we're also interested, and it would be very exciting to see what happens with other fairness notions. Can we make this better? Can we get an algorithm that gets envy freeness and also show something similar for some setting? Can we take algorithms where we already know that equilibria exists and give a property on how this must look such that these equilibria are with respect to the truthful valuations? So there's a number of questions you can imagine, and we have no idea on most of them actually, because this is, I believe, the first paper to try this stuff. So yes, I think it was nice structurally, and I liked working on this. And I was personally very happy that we could come up with some results, and hope that I could spark some interest also from your side on these things. Thank you very much for listening. And this is all I have. So let's conclude here. And if you have any questions, go ahead.